Hello, Algebra students. We are going to start this video looking at reasoning from exponential representations. I want to start first with our general equation. So we are looking at lesson 512. Okay, I've got to move this. It's not letting me move it. Okay, we'll see what we can do. All right. So our general function, our general equation for our exponential functions is y equals our starting value times the multiplier, that's your growth or decay factor, to the power of x. So we are going to rewrite this using some more common variables. A is our starting value, b is our multiplier. Okay. So what we are going to explore through this lesson is how changing the value of A will impact your graph, and how changing the value of B will impact your graph. So I'd like to show you this. I'm going to put 4 different graphs up, and I want you to look at these 4 graphs. We have our starting value on all 4 of these is 50. Our multiplier, though, here it is 2, 3, 3 halves, and 0.5. So the red one right here, that's our multiplier of 2. Is that increasing over time or decreasing over time? Yeah, it's increasing. The blue one with our multiplier of 3 is increasing even faster. 3 halves is this green one that is also increasing, but not as quickly as the red one or the blue one. The fourth one here, purple, with our multiplier of 0.5, is decreasing. So what does the B value, our multiplier, our growth or decay factor, do for us in our function? Well, when B is between 0 and 1, that is when we have exponential decay. So that's our decay factor. And really, the closer to 0, the more rapid that decay. Okay? Then we are going to look at what happens if B is greater than 1. That is our growth factor. And the larger the value of B, the more rapid the growth. Okay? The closer to 1, either a decay factor or a growth factor we have, the closer to 1 that value is, the less intense that decay or that growth. It's a more slow progression. Okay? Keep that in mind as we look at additional questions. So now let's take a look at what happens when we change the A value. So I have 3 functions here. we have 4 to the x in all three functions. So our multiplier is 4. 10, 40, and 100 are the different starting values or intercepts we have. So here we're looking at a starting value at 100, at 50, at 40 and at 10. Okay? If you notice, each of these curves, the blue, red, and black curves here, are very consistent when you compare them to each other. They follow very similar paths, and that's because that multiplier is the same throughout. The only thing that changes is what we call the vertical shift. So as our starting value changes, that place on the y-intercept changes. So we can go back and summarize then that our a value determines the vertical intercept. Not an S, a C. Okay. We call this the vertical shift. So let's see what this looks like in action. Okay. So here we can make decisions about this graph. We can determine which function relates to which image in the graph. So here we have a function with a bacteria population, and that function is Q of t equals 5,000 times 1.5 to the power of t. The number 5,000 is our starting value. It is that initial population at time equals 0. The 1.5 indicates that the bacteria population increases by a growth factor of 1.5 each hour. So we can see that population start right here. If I have two additional functions, how does that growth factor of 2 and that growth factor of 1.2 compare to our original of 1.5? So the green curve, that's the P of t equals 5,000 times 2 to the power of t. The red is the R of t equals 5,000 times 1.2 to the power of t. And then the blue one is that original for us. Q of t equals 5,000 times 1.5 to the power of t. So we can make some comparisons and determine that the bacteria population in our P function is increasing at a more rapid rate than our original function. All three graphs start at that same value, same starting value, but one grows more slowly than the other and one grows more quickly. And if we compare those values, 1.2, 1.5, and 2, remember I made the comment that the closer to 1 your value is, the less intense that growth or decay. The larger your number is, greater than 1, the more intense that growth or decay. Well, for greater than 1, it's growth. The more intense. So when we have a decay rate, it's that closer to 0. Okay. And that is lesson 512. We can look at our A values and our B values, and we can use that to help us identify relationships in a graph, determine which function is growing faster or slower than another, and we can understand what that multiplier tells us and what our starting value tells us.